Good afternoon, everybody. This is Tang from Lyft. I'm leading growth science. And then today, I'm going to introduce you how we leverage machine learning to scale Lyft growth. And by the way, I appreciate you sitting here. I think those folks outside, they will miss the most fun part of today. All right. How many of you actually take a Lyft to this conference today? Okay. Thank you. So if you haven't tried Lyft, try it on your way back. So as you know, Lyft is a rideshare company, and then it's actually a two-sided marketplace involving both riders and drivers. Here I show you two charts, which is number of active riders and the number of active drivers, how they grow since COVID. And then as you can see, the trends are pretty similar. They are very coupled with each other. Right? So this actually poses some challenges for us. We really need to balance between rider growth and the driver growth, because if we have too few drivers, then riders will have very long wait time, and naturally, you will see a high price for the ride. On the other hand, if we have too many drivers but not enough demand, then drivers would be idling most of the time. Naturally, they would earn less. And then because of many regulations, there actually some minimum requirement, how much they need to earn, which actually cause a lot of complexities. I want to emphasize that this undersupply to oversupply, this could change even within hours in a day at different regions in a city. And then within 1 week, 1 month, every quarter, this could swing very dramatically. And then when you focus on the growth of both demand versus supply, the time scale is very different. For a rider, it could take probably just hours or days. Download the app, you take your first Lyft ride, right? But for a driver, starting from the application to go through the background check, have some vehicle checking, make sure the vehicle information is correct, then serve the first ride. This could range from days, weeks, months, or even years. And then normally when you look at the marketplace, whenever there's anything happens, demand would respond immediately. Right? That's what we see with like a pandemic. Demand immediately dropped, but then for a short time period, we're seeing too many drivers are still driving there. Like the utilization, like they are idling probably 60% of the time. So we saw that like supply tends to lag behind, typically like months behind how demand responds to these external like changes. So this actually poses a lot of like challenges for us, how we want to grow both supply and demand at the same time, how to coordinate that. And then there's a couple of requirements. The first one is it needs to be flexible. So depending on the supply, oversupply, we want to shift, like say, how much effort we want to focus on one side versus the other. And sometimes we even say, okay, when there are too many drivers, we actually need to limit, like say, stop growing the supply side, try to focus on the demand side, right? So it needs to be flexible for us to handle kind of these different situations. And then the other one is it needs to be scalable. You wouldn't believe that in the early days of Lyft, we use a spreadsheet to track how much a bonus each driver accrues. And by each Friday, our PM would upload this CSV spreadsheet into a system, try to pay out the drivers. That's doable only during the early days when you have probably a few hundred or like thousands of drivers. But when you have like say hundreds of thousands or millions of users, you need to build some automation to make sure the system is scalable to handle that. Lastly, all the levers, all the system we build needs to be efficient because we want to grow our business, number of users, number of rides, we want to grow profit. We want to make sure all these like growth systems and levers are cost effective. Here is an overview about the growth platform we built. On the top right, that's a paid acquisition platform. It's essentially like Lyft trying to spend hundreds of millions of dollars across different advertising platforms like Facebook, YouTube, Instagram, TikTok, trying to acquire users to the platform. And then we actually use some we built a multi-agent system of like contextual and continuous bandits. And then to do this budget allocation to manage our thousands of kind of advertising campaigns. It was published in the KDD conference last year. So you can take a look. Then on the top left, there's a communications platform. It's like, so once a user is activated at Lyft, how do we send out email, text messages, app notifications to keep them engaged with our product? So this involves a lot, like say, multi-armed bandit and context bandit to decide which user, what type of message we need to send to this particular user, right? So, and then on the right, there's an incentive platform. So that's what I'm going to talk a lot, go deeper today. But essentially, this is like trying to decide what type of coupons we should give to a rider, what type of bonus we should give to a driver, so that this user would like be highly engaged with our products. And then underlying all this platform, there's like, we have a data platform to really power all this customer data, as well as some gross machine learning framework. Due to the time limit, I will just focus on the incentive platform. One thing I want to call out is that the whole growth platforms, we are essentially spending billions of dollars trying to grow our business and send, like say, running all these incentive campaigns, sending billions of messages to our users. So this is actually contributed a significant portion of the Lyft growth. Here, I want to give a very high-level abstraction of the problem, like the growth problem. Paid acquisition, communication platform, incentive platform. It involves two components. The first one is we want to leverage machine learning to predict what's the effect of treatment, right? So here, the treatment could be some ad exposure, could be sending user a message, or could be some incentives, like give a coupon to a rider, give some bonus to a driver. And then based on the treatment, they might either like take a Lyft ride, they serve a ride, right? So, and then there's a cost associated with those because all these advertising and the incentives involve true dollar monies, right? So we're spending quite a lot of money just like trying to engage with these users. And then even for communication messages, there's unsubscription costs as well. If a user unsubscribe, then we lose all the possible ways to connect with them again in the future. So that leads to some LTV kind of reduction. So that's more like using machine learning to figure out the treatment effect. And then the second step is saying that based on the treatment effect, we're trying to maximize certain objective function. Could be number of new users we acquired, could be number of rides these users take, subject to certain constraint. The cost has to be under certain guardrail or budget, right? So, okay, so here I will use incentive platform as one example. Like how do we really use both machine learning and Bandits to address these challenges? So what makes up the incentive platform? First, there's a population management, essentially decide which users are eligible to receive some incentive. Then there's one component really just send out coupons, send out the incentive to our users and observe the outcome. Then underlying that, there's HT modeling, trying to figure out what's the treatment effect for each individual user. And then there's also allocation piece, like based on the HT model prediction, trying to figure out how do we, like say, suppose we have 1 million budget, how do we want to allocate all this spend across different users? For each user, what should be the right coupon to give to them? And then of course, there's some reporting trying to measure the incrementality, what's the spend, what's the business impact of this incentive campaigns. Here, actually, this is a very interesting problem because it involves both causal inference and the reinforcement learning. So here you can think it this way. The HT models are essentially trying to figure out, because we give a coupon, how this user behavior will change. Then we run the optimization. So essentially, we take an action trying to give the coupons to these users, and then send out the coupons. Then we observe the outcome. Then we will continue this process. So we take one action, observe the outcome, retrain the model, and then kind of take another action. So it's a classical like a reinforcement learning setup. And here I talk about HT model. What exactly is a HTE? So here I give you a formal definition here. So let's use Y as the outcome. So this could be rise or driver hours. And then X is some feature vector associated with this user. Most like say, in the past 28 days, how many rides they have taken, how do they interact with our product, and potentially in certain scenarios, there's a little bit like profile features about these users as well. And T represents treatment. So let's use a coupon as one example. It's like a rider receiving a coupon. That is considered as one treatment. If they don't receive a coupon, that's not, then there's no treatment for them. And then we can try to figure out the response from treatment. So given certain user feature, given the treatment, how many, like say, how many rides this rider would take. And at the same time, we could also figure out, without the treatment, without giving the coupon, what, like given the user features, characteristics, how many rides they would take. The HTE here stands for heterogeneous treatment effect. It's trying to say, okay, by giving this particular treatment, how many incremental rides I would get from this user. So this is exactly the core, like the underlying kind of objective, trying to figure out the incremental effect, right? So because we're trying to figure out the incremental effect, this is different from classical supervised learning. In classical supervised learning, you have X, you have Y, right? So you build a model to predict from X to Y. So the Y is directly observable. But when you are trying to figure out the incremental effect, a user either has to be in the treatment or in the control. You cannot observe the exact incremental effect. So it's different from classical supervised learning. So that's why here, we could never observe the true outcome. So that actually poses quite some challenges for HT modeling. Here, actually, this has a lot of like active development, what type of models we could use. And then to give a sense, we here give you one toy example. So like say, we have 6 different users. And then from past some A/B test experiment result, some users like receive a treatment, some do not, right? So, and then the treatment could be 10% off coupon, 50% off coupon. And then based on that, we observe the outcome. They have like a number of rides they take, right? So this is from past experiment data. We have this like training data. Then we build some HT models. Based on that, we're trying to estimate the incremental effect by giving a user a coupon. And then we can predict for any user, suppose they have certain characteristics, giving them a 10% off coupon, like for user 7 on the right, we expected the incremental rise is 0.5. If we give a 50% off coupon, that is 0.8. So essentially, we can figure out for each user, all the possible treatment, what are the likely kind of incremental effect there. And then we have this prediction. We can say, we can solve a linear program. I want to maximize the incremental rise. So that's our objective function. Maximize the incremental rise from these users, subject to certain constraints, saying that my total cost from all this treatment, essentially like say all the total spend on coupons, that has to be under a certain budget, right? So, and then we can plug in different numbers of budget that will naturally give us a cost curve. So essentially, depending on how much we want to spend, we know that how many incremental rides we would take, we would get from these users. Then based on other, like say, undersupply, oversupply, we can dynamic change what should the budget for our incentive campaigns. So based on the budget constraint, we can decide which user would be eligible, would be qualified to receive these coupons to maximize our kind of incremental rise. Cool. So that's like a very high level idea about HT modeling, how to use like this causal model, causal machine learning to figure out the incremental treatment effect. But it's actually harder than it looks. Training all these HT models actually require exploration. So suppose our optimization saying that for any new riders, we should give them a $100 coupon. But then that would give you some trouble because when you try to retrain the model, you find that I have no idea what the rider would do if they do not receive any coupon, right? So that means we have to do some exploration, like certain users would receive treatment, certain users would not. So this is a classical exploration, kind of exploitation you have to balance. We essentially resort to Bandits to trying to solve this problem. And then two classical ways. One is using some epsilon greedy. So in order to maximize our business outcome, we allocated 90% of kind of users based on the allocation policy. Like say, this is what we believe would be maximize the business outcome. Then reserve the 10% of users in that just to random drop. Like say, they would randomly receive some coupons. And then some of them would not receive any coupon. So this would generate complete random data. So that's a nice property. And it's very easy to set up and understand. But then there's a downside of that. Because for the 90% of the user who are actually receiving all this treatment following the optimal policy, you cannot use them for trading because the sample is biased, right? So, and then also like there's inefficient partition of the data, right? So if you want to allocate more traffic for random exploration, that actually has a dollar cost there, right? So because you're just trying to random give people coupons in order to retrain the model. So there needs to be a balance there. Then we resort to Thomas sampling. So here we're trying to figure out the posterior distribution, like say what's the reward like look like. Then from the posterior distribution, we try to figure out figure out the optimal decision. And then in this way, we would be able to use 100% of the data. But then it also kind of, this is definitely more efficient than this epsilon gradient approach. But then because it's not completely random, you have to develop some propensity score for each instance. And when you train your machine learning model, you have to like align this inverse propensity score to the weighting to figure that out. Of course, there's another one is that you need to, for Thomas sampling to work, you're drawing from a distribution. You really need to understand the uncertainty of this posterior distribution, right? So all this adds some model complexity there. So we tried both this HT modeling plus Bandits for our incentive campaigns. In general, we have been observing, like say, 20 to 50% efficiency gain compared with just random dropping some coupons to our users. When you multiply the dollar spend, that actually is a meaningful business impact for the company, right? So here I'd like to share a couple lessons we have learned by in the past few years building these growth platforms. One key challenge we faced in the past is how can we shorten the machine learning feedback loop, right? So because for example, for the HT modeling, we don't observe the ground truth. So it's not like classical machine learning, supervised learning. You have mean squared error. I can easily train a model and then probably change the parameter and then add some features, switch from support vector machine to deep neural. I can figure out what the performance look like. But here for HT, no, you don't know the ground truth. You either know that given the treatment, what's the outcome, even without treatment, how many rides it would take. You don't know the exact incremental effect there. And then there's some metric, like say, some metric allow you to assess the ranking of this instance, but they would not calibrate what's a prediction accuracy. But the accuracy itself, it matters a lot for us because we have this budget constraint, right? So, and then if that scale is off by 2x, then that actually leads to a completely different allocation. So during the early days, actually it's really challenging for us because if we really want to understand what's the impact of adding one single feature to this model, that would go through a long process. Like we add one feature, train the HT model, run the optimization, decide, then send coupons to our users, and likely we will run some A/B testing for like say 2 to 4 weeks or even longer, and then we figure out, okay, whether or not this feature is useful. As you can see, this slow down the whole process for innovation. That's impossible. So we have to figure out some other ways. And then that's what we come up with. So let's try to have reuse some existing data, use off-policy evaluation to understand how effective a new targeting strategy would be. So off-policy evaluation, you can consider that's some form like a back testing, right? So the key part is that you need to figure out, like say, suppose I have old policy, now I have new policy. You try to look at all these data samples in the past, somehow these two policies agree with each other, but then you need to apply some weight. You try to kind of assign more weight for those instances such that the two policies tend to not agree with each other, right? So, and then in that way, it will give you a sense about what the new policy would look like by looking at the past data. But of course, there's one key requirement here is that there needs some form like random exploration. Otherwise, the bottom, whether or not the old decision agree with the new decision, that probability becomes 0. Then you essentially this will do not work. So it need to have some exploration to work. Off policy evaluation, it enables us at least to give us some directional signal saying that whether or not a certain targeting model actually makes sense. And then there's another challenge is that we have kind of all the different variants, coupons, different incentives, like say 10% off 5 rides, 25% off 1 ride. As you can see, these are probably there's some dimension that are more or less correlated with each other. You would expect like maybe 50% tends to have more incremental effect, and the number rise, the higher, then the larger the incremental effect would be. If you use just like existing kind of machine learning HT models, then you have to build essentially 2 models. One is to predict what's the incremental effect of the treatment. Then the other one is to predict the cost. And then depending on how many treatment you have, you would easily get up, like say, dozens of different models. It's really difficult to maintain and to train. And especially when you want to tune all these models, it just requires way much more effort. So rather than try to have a separate model for each, like the incremental effect cost for each treatment, we try to build a neural network. So essentially by sharing certain layer, like latent layers there, and then we can just build one single model to kind of do multiple predictions about the cost and benefit. And it also allows us to parameter, basically like have some parameters in the treatment, saying that like given the treatment like X% of Y rise, what would be the incremental effect look like? So we just deployed one architecture based on some recent work like the DragonNet, that's like for this HT modeling. It shows very promising result when we deploy that. But then there's one unexpected observation which is really killing us, is that we found that this deep neural network has very high variance. So, so this is a true story we had. Typically when we launch like these big model changes, we would like to run AA tests, just want to make sure everything works fine. And then with the DragonNet, we run AA tests, we saw a 10% difference. Using the same training data, the same model, it's just like the random seed is different. And then it'll give us like a 10% difference, a statistic difference for AA test, right? So when your model variance is so huge, then it's really difficult to understand. Like, do I make something right, or do I just hit something by chance, right? So that means like we have to, in the end, we have to spend a lot of efforts trying to reduce model variance, like tune the parameters of a deep neural network, and then also try some ensemble to make sure the performance is relatively stable. And then we'll also even like move certain component, like we try to understand the feature importance. We try to use a simpler like HT model rather than using deep neural, rather than using a neural network to do that. So in that sense, we can minimize the effect of this model variance, but at the same time, we can try to get the best performance like from these modeling efforts. All right, so cool. So that's pretty much for my talk. A quick recap is that, as you can see, we are trying to leverage both causal inference and Bandits to scale Lyft growth, right? So if you want to remember one keyword from this talk, that's the HT model. So just want to remind you, HT model is trying to predict the incremental effect of the treatment. So it's different from classical supervised learning. The outcome is not directly observable. So this is actually a very active research field, starting from very easy meta-learners to causal tree, causal forest, and now to deep neural networks. And it originates from like statistics and economics, and now it's really merging with machine learning. This is By understanding this causal impact of different treatment, there's definitely a lot of applications across the industry. And then the other one is about the trade-off between exploration and exploitation. Thomas sampling tends to be, I would say, the most really simple, easy to interpret. It has been widely used at Lyft to handle this multi-armed bandit and context bandit problems. And then lastly, the lessons we learned is that in order to really iterate and innovate faster, we have to shorten the machine learning feedback loop, either by through some off-policy evaluation, by reducing model variance. There are some other lessons as well, like for example, we also need to do some data versioning for some of these machine learning models. I'm happy to chat more on those. But overall, as you can see, we're spending billions of dollars trying to grow the Lyft business, and the machine learning is a backbone there. And then, so that's pretty much for my talk, and thank you. Yep.
Any questions?
Hello, thanks for the presentation. So I'm wondering, how short could you get the feedback loop? And if you could speak a little bit about how you guys design the treatments. So does that come from business? Do you guys do some suggestions? So how is that interaction?
Okay, so I would say the first part is how short the feedback loop could be. I think I would say before we have this off-policy evaluation, it's painfully long. It's like take 1 month to really understand. Like essentially 5 minutes, you can make a code change. And you need to wait for 1 month in order to understand how much impact this code change could be, right? So that's why we basically shift the efforts. We need to have some off-policy evaluation. And then once we have this off-policy evaluation, it would give us some signal. I would say there's still some bias and limitation with the off-policy evaluation. If there's like a big impact, then directional, like so when you run the simulation, that would give you a sense of how much impact that could be. And then normally we try to use off-policy evaluation to pick those big ones, implement that, and then we need to run A/B testing to validate the result, right? So, but of course there are certain ones like it's really neutral, then that's a little bit TBD. It's more about help us prioritize or figure out what type of changes to the models could have a larger impact there. Right? So the off-policy evaluation would reduce more like say multiple days to 1 week to understand most of these targeting model changes. So that's one. The second part is asking about how do we come up with the treatment. I would say is working with product managers, then we design different type. Like for example, for incentives, we have different type of incentives, and then there are certain ones like say you have X% off coupon, X dollars percent off, X dollars off coupon. Then there are also some more complicated ones, like say you need to take certain action in order to get some reward. So it's more like a joint effort. And then whenever we introduce a new treatment to the inventory, we need to do some exploration first in order to do some targeting.
Yes, so the whole usage of coupons to grow business and all that, your method, does it apply to all the other businesses that use coupon as a way to generate more sales, or is there something specific to Lyft that is particularly applicable for what you're doing?
I believe HT definitely could be applied to other domains. Even within growth, say, for many of these, we're sending out the messages, we're also trying to understand the incremental effect as well, right? So, and then I can easily imagine all these recommendations you should try to really understand what's the incremental effect. Because I can give you one total example, say when you're working on e-commerce, if you buy a TV, you have a high likelihood about buying a TV stand. Do we still want to recommend a TV stand, or do you want to recommend something? Because of the recommendation, you actually will change your decision, right? So I think trying to change from simply the outcome to the incremental treatment effect, this would be really a big this could apply to many other domains. And especially when you involve some costs associated with that, I think this tends to be more effective.
On TV, I won't be buying an incremental TV, so it probably won't help.
I mean, from TV to TV stand,
stand.
right? So,
So maybe I missed this, but how was the coupling between the drivers and the riders captured? Were there separate models for these, or were they together in the HD model?
it's captured more at the higher level.
The
right? So,
optimization level.
like we try to build all these, like say, models for riders and drivers separately, and then the key part is saying that how much budget we would give to riders or drivers. Like say, in one region at a certain time, we want to focus more on the rider side, then we will dial up the budget spend. Or like we need to get more supply, then we move the budget to the supply side, right? So the budget is the way, how do we couple these two?
Okay. Thank you.
Great. Well, thank you so much. Appreciate the presentation, Lei.